Welcome to Energy Lesson 11. This is a triple only lesson and it's a triple only required practical on thermal insulators. My name's Mr. Pratt, Director of Science. Before we start then, you're going to need a pen, paper or an exercise book. If you have got any graph paper, it'll be useful. If not, don't worry about it. You'll need a calculator, and unless you're needing to watch this video on your mobile phone, get it out of the way, or get it on silent at least. Try and avoid all the distractions that you can. Into the starter then, 2 minutes. It's a 3-mark question, just to have a look at how well you can remember your graph skills. I'll give you 2 minutes. Halfway through your time. On part 2 of the question, try and get both marks and not just one. Let's check first that we know what it's a graph of. We've got time on the bottom, 1, 2, 3 hours. Temperature up the side, so we've got water's heating up as the sun's on it outside. Part 1, how long does it take for the water to reach 37 degrees? So carefully find where 37 degrees on your y-axis is. Go across, meet your best fit line and go down, and you should end up with 1.2 hours. If you've converted your 0.2 into 12 minutes, that's fine. So that would be 0.2 divided by 60 minutes would give you that 12 minutes. So that's straight 1 mark. There's no tolerance there. You've got to get exactly the right answer. Part 2. There's 2 marks we're after. The first mark's pretty easy. As time goes on, the water temperature increases. So increases, gets hotter, that'll get you 1 mark. But it's not going up at a steady rate. If the temperature was increasing at a steady rate, that would be a straight line. It's not, it's curving over. So you need to explain the fact that it's curving over. So the temperature is increasing faster at the beginning than it is later on. So on the mark scheme, they've got rapidly at first, then increasing at a slower rate. So increasing, but the rate gets slower would be fine. Look at the outcomes then. We need to be able to describe this experiment, including safety precautions. And the experiment is about the effectiveness of different insulating materials. So how good they are at preventing conduction of heat through them. 2 parts. We're going to compare different materials and we're going to look at a factor of 1 material as well. So we'll just tackle it in 2. This is how the required practical is written down in the specification. So let's start from that. Investigate the effectiveness of different materials as thermal insulators. We're going to look at bubble wrap, newspaper and cotton. And the factors that may affect thermal insulation properties of materials. So part 1, compare different insulating materials to each other. And part 2, how does the effectiveness of an insulating material depend on its thickness? The only questions that I've seen have been about thickness in the exam, so we'll concentrate on that. 2 parts then, just in summary. Record this if you want. So we're going to look at comparing different materials. We need to be very careful that we're testing fair, so we need to consider control variables. And then we're going to have a look at a factor, and the factor we're going to pick is going to be the thickness of the material. Basic setup looks something like that. We've got beakers there with hot water in, insulating materials around them and a lid. The reason we need a lid is otherwise we're going to end up with convection. We're going to end up with the hot air above our hot water rising as it gets less dense, and we'll lose heat that way. We want to restrict that because we're concentrating on looking at preventing the conduction of heat through the material. Risk assessment, 2 things to mention. You're dealing with hot water, so great care using hot water from the kettle. Make sure that it's cooled down long enough at the end of the experiment. If you've insulated it well, it could still be hot enough to burn you. If you do burn yourself, you need to get it under cold water as quickly as possible. We're using glassware as well, so there's an element of risk with breaking glassware, so take care with breakages. If you do have a breakage, make sure that you're getting someone else to clean it up, dustpan and brush, instead of your natural reaction to pick up glass with your fingers. Method then. You can either record this now, you might need to pause the video, or when I'm demonstrating it to you, you might want to make a note that way. Either way is fine. So we're using boiling water, 100 centimetres cubed. It doesn't have to be that amount. It could depend on the size of the beaker that you've got. When I do it, I use a little conical flask. It just makes the lid a little bit easier because you've got a smaller surface area on the top. Piece of cardboard as a lid. Need a hole in the cardboard for your thermometer. Thermometer goes through. Make sure that the thermometer bulb is inside the hot water and not over the top of it. I'm going to start recording the temperature at the beginning and then take it every minute for 10 minutes. So we'll get it cooling down over 10 minutes. And we're going to do that with different materials. I'm doing it with 3 different materials. Control variables, so things that we've got to keep the same. Starting temperature, that's sort of optional, but it does make your graph work easier. The volume of the hot water and the thickness of the insulating material. We want a fair test here, so we want the 3 insulating materials that we use to be the same thickness. Let's talk you through then the required practical. So the title of the required practical is investigating the properties of different insulating materials. We're going to do this as 2 parts. Part 1 is going to be investigating different materials. So the materials that we're going to look at are bubble wrap, newspaper and some cotton. There's quite a focus in this required practical on your scientific method and variables. So let's talk about those to start with. The thickness of the material, I've already got it and measured it, and the thickness of the materials that I'm going to use is going to be the same for all 3 of them, and the thickness will be 0.5 millimetre, 0.5 millimetres. This is called a micrometer, and it will measure very small volumes, thicknesses, and I'll show you exactly how that works later on, but I've used that to work out the newspaper thickness so that I know I've got enough newspaper pieces that add up to 0.5 millimetres. Control variables then, thickness, the volume of hot water that I'm going to put in. So we're going to put hot water in there straight out the kettle and then plot, once we've got readings from 0 minutes to 10 minutes as the temperature drops. We'll do it for bubble wrap, we'll do it for newspaper, and we'll do it for cotton. The volume's going to be the same, the thickness is going to be the same, the starting temperature I'm going to make sure is the same, the times that I'm leaving them to cool down are also going to be the same. The independent variable here is just the material type, and the dependent variable is going to be the temperature drop. I've marked on just a black line to make it slightly easier for you to see. of 100 millilitres. Flip the kettle on, just out of view, but you'll hear it click on, switch off. I'm going to put that in there, going to insulate it. I'm going to put a lid in each one so that we're not losing heat from convection. So I'm just going to bob that in there once I've got the thermometer in. Whatever starting temperature I end up with, this one is the starting temperature that I'm going to use for the 3 different materials. Careful I don't burn myself, and I need to take care with the glassware. I don't want to squash it too much because that will squash the thickness. I've had to do an average thickness for the bubble wrap, obviously, because there's bubbles in some places but not everywhere. Pop the thermometer in and use that as a lid to stop our heat loss through convection. I just hold that up to the camera, you can see the temperature starting to rise there, it's above 80. Once it's settled, now I've managed to lose my lid that slipped in, so instead of starting again, I'll change my plan. And I'll just make a newspaper lid, and I'll use the same newspaper lid for all of them, just to stop the losing heat loss out the top. That's okay. So we're settling on 88 and it's stopped, so I'm going to start there. So the starting temperature for the bubble wrap, so that's times 0, 88, and all these readings are going to be in degrees C. I'm only going to measure to the nearest degree because that's the resolution on the thermometer, it's just measuring to the nearest degree. I'll just do a couple of minutes and then I'll cut the video so you're not sat here waiting ages. If you're doing this yourself, you'll just have to sit through it and do it. You could set up all 3 in one go if you were doing it yourself and working in a group. So you'd be plotting them as you go along, it'll be 3 times as fast. Just coming up to 40 seconds. At the moment, just drop 1 degree. Fairly quick it might. Yeah, it looks like it's going to be dropping too. We're just dropping down towards 86. Yeah, bang on. 86. So it's dropped 2 degrees in 1 minute. I'll do one more on the bubble wrap and then I'll stop the video and move on to newspaper. I will get all the readings for you though, I'll write them down. I'm also going to use the same thermometer for all of the 3 different materials as well, just in case that there's a systematic error with the thermometer, with it being a degree out or half a degree out each time. It's just dropping down towards, it's just below 85 now. I might try and read to a half degree if I can. Yeah, it's dropped to 84.5, so I'm going to put an extra decimal place on those. I'm going to stop the video now, but I'll carry on taking the readings for you and pick it back up with newspaper. I've completed the results all the way down for bubble wrap, and it's dropped down after 10 minutes to 77.0 degrees, so it's dropped 11 degrees. I'll just write that, so it's 11 degree total drop. I'm just getting ready to start with the newspaper. It's slightly too warm, it's on 89 at the moment, and I want it to start at 88 so that I've got the same starting temperature for all 3. Probably a little bit hotter because the glass conical flask was already hot. I've got the same lid, bit of newspaper shoved in the top. I've got the same thickness of newspaper, so I've got 10 sheets that's given me equivalent of 0.5 millimeters, the same water volume. The only thing that's different is the material that I've used as my insulator. Almost there. And go. So it started at the same temperature, 88 degrees. I'll just do a couple of readings for you, finishing off myself, and then we'll go on and do cotton. You could do this practical with as many different insulating materials as you like. It's only time that would prevent you doing lots. The manufacturer would do something similar when they were testing the insulating properties of outdoor clothing, fleeces, coats. Got 10 seconds left. It's already down to, oh, it's only on 87.5. Sorry, 86.5. I'll carry that on, but it did drop slightly less in that first minute. I'll do one more and then I'll finish the rest of them off myself for you. While I'm waiting, I've got a single sheet of newspaper using this micrometer. You put the newspaper into the gap and you turn the barrel, and what it will do, it will tighten up, and you can read the scale on what's called a vernier scale. You can read the number off, and it gives a single sheet of newspaper as being 0.05, 85 degrees. It's just slightly better than the other one. That's how I calculated that I needed 10 sheets of newspaper. So it's a very accurate and precise, because it's measuring to the nearest hundredth of a millimetre, way of measuring small thicknesses. On to the cotton then. It's all ready to start the first reading. It's just reached 88. Off we go. So just going over the independent variables again. Thickness of your insulating material, water volume, starting water temperature. While we're waiting for the first minute's temperature, I've just done a quick calculation. So the bubble wrap over 10 minutes dropped 11 degrees C and the newspaper dropped 9 degrees C. Looking at that there, there's some issue there with anomalous result. It was dropping half a degree, then it's dropped 1 degree, then it stayed where it is. I'm suspecting that that one there is anomalous. It'll show up on the graph when I put these on a graph for you, a cooling curve. Just coming up to the first minute. Okay, it's dropped to 86.0. I'll just do one more and then finish them off for you. It's definitely dropping faster, this one, than the newspaper. You possibly wouldn't have thought of newspaper as being the best insulator. Maybe think why that might be, if it is the case, when I finished. Okay, that's 84.0. So far, it's been the worst insulator of the three that we've done. All done then, apart from my messy sheet. The cotton dropped a total of 11.5 degrees C over 10 minutes, so there was a slight difference, not much, between the bubble wrap and the cotton. That's part one done, where we've investigated the different materials. I'll get these results on a table and we'll do a cooling curve graph, and we'll look at how a graph might give us a little bit more information than we've got there already. Then we'll come back and we'll look at part two, which will be changing the thickness of one insulating material and see how the thickness affects its insulating properties. Here's the results tabulated then. I've put in red that anomalous result for newspaper, so it's dropped 1 degree and then stayed the same. That's either a random error where I've misread the thermometer, or because I didn't stir, we've perhaps got a slight separation in the temperature, and when I've shaken it, it's caused it to mix again. So we've got that one. You could either miss it out or just put it on the graph and mark it on the graph. So we've got them all dropping. You can make a conclusion already from that, without plotting the graph, that the newspaper was the most effective insulator there, because we've got the smallest temperature drop over 10 minutes, with bubble wrap being the second most effective and cotton the worst, but really there's very little between the bubble wrap and the cotton. Here's the results then as a cooling curve. So time along the bottom, temperature up the side. So we've got three plots that we've got, one for the newspaper that's in red there, one for the bubble wrap that's in blue, and one for the cotton that's in green. And we can have 3 separate curves for those. So let's look at graph skills a second, and I'll talk you through what we can do with this graph. So we've got us cooling curves plotted. We've got newspaper, that's the top one, the orange one, bubble wrap, and at the bottom we've got cotton. Drawing a best fit curve, not easy, but if you've got a curve in that direction, it's a lot easier if you turn your paper around. Give it a bit of a practice. So I'm going to do the newspaper one first. Just going to mark that. We've got the same starting point for all 3 lines there. I'm just going to go for it. Not bad, slightly high there, not going to worry too much. Let's go through that one. Do a better job of that one, and then the bottom one. Just going to change that slightly. If you do that on the exam, you must make sure that you make it very obvious which one you don't want the examiner to look at. So we've got us cooling curves. So you can see that the newspaper one drops more slowly than the other 2. So that's going to be our most effective insulator. You could be asked to do some other bits of work with this as well, like gradients. It could ask us, for example, to find the gradient of the newspaper line at time 2 minutes. So let's find time 2 minutes, that's there. So if you're finding the gradient, you put in an estimated line on there with the correct slope. I'm going to carry it on until it meets the axis. Got a bigger ruler. It does meet the axis quite well, about 10 there. So now we've got this triangle, and the gradient of that tangent that I've just drawn is going to be the change in y divided by the change in x. So the change in y is 2, 4, 6, 8, 10, 12, 14 degrees. So we've got 14 degrees divided by the change in x, which is 10 minutes. So we've got 14 divided by 10, which will give you a gradient of 1.4. Be at least 3 marks for that in the exam. What does that gradient mean? Well, that gradient is the change in the temperature, so it's degrees C, divided by minutes. So it's actually the temperature drop that we have per minute. So we've got 1.4 degrees C dropping per minute. If you were to do
the gradient of the bubble wrap, I'm not going to do it, it will be dropping more quickly, so you might end up with an answer of say 1.6 degrees C per minute. So you're losing more temperature per minute.
This time we're going to look at just one material, and I've picked newspaper to do this because it's the easiest to put layers on. The part 2, investigated insulator thickness. So we want to see how the thickness of it affects its ability to keep heat in. Control variables, same volume of hot water as before, 100 centimeters cubed. I'm going to use the same starting temperature as before, 88 degrees C. This time I'm not touching any other insulators apart from newspaper. So at the moment there's one layer of newspaper on there. It's quite difficult because you need a little bit of overlap just to stick it down, but I've tried my best. I'm going to use a lid again so that we're not getting heat loss through convection. So once we go in, that'll go in the top. To start with, we could do this without any insulation at all, and then we'd have a thickness of 0. I'll probably do that last and I'll add it in for you so that you've got it afterwards. At the moment, that's one layer. I measured the thickness with the micrometer, so one layer is 0.05 millimeters. I'm going to do one layer, 2, 3, 4, 5, 6. I've already put the result down for 10 layers because we had that in part 1 of the investigation, where we had the newspaper, it was 0.5 millimeters, so it must be 10 layers, and we had a temperature drop of 9. So we've got another value which might be quite nice to put on the graph as well to see if it fits in with the pattern. This time, to avoid all sorts of lines being on one graph, I'm going to do it slightly simpler. I'm only going to record the temperature drop for the full 10 minutes. So I'm just going to leave it 10 minutes and then take the temperature drop at the end. Hot water in then. Let's look down and just see my line, which marks my 100 millimeters, tiny little one. There we go. Let's wait for it to get up to our 88. Oh, it's almost there. So they're all starting at 88. Just put that on my bit of paper. Start temperature equals 88 degrees C, just in case I forget. So I'm going to start that now. Then after 10 minutes, I'm going to record the temperature that it's dropped to and just write down the temperature drop. So it might drop, say, 20 degrees. And then I'm going to put the whole thing, start again, but 2 lots of newspaper on, which will give me that double thickness. And I work my way down, and then we'll see what the effective thickness is. It would then allow me, when I've finished, to do a graph of the independent variable, which is going to be the thickness. That's the thing that I'm changing, the thickness in millimeters. And I can plot that against the temperature drop in 10 minutes. That'd be degrees C. So for example, if I put on my 0.5, that'd give me the 9 degrees. So I've got one line on there. Okay, I'll fill in all the results for you and I'll flip back and we'll see how we've got on. A quick look at the results before we move on. It's worked in that every time that I've increased the thickness, I have got a smaller temperature drop all the way down. We'll have a look how it looks when we put it on a graph later, but we are, from what I can tell now, I can't see any anomalous results. Those two are a bit close together, but it is working in the thicker your insulating material, the less of a temperature drop we've got. Here's the results tabulated then, with thickness first in millimeters and then the temperature drop just recorded for 10 minutes. Let's see what graph work with that. So we've got thickness on the bottom from 0 up to 0.50 is the highest reading that we've got. You can see that that point that I used from part 1 of the investigation seems to fit in quite nicely. So we'll put a bit of a best fit curve on there. And then I've got a question for you. Dave makes the following hypothesis. Doubling the thickness of an insulator doubles its effectiveness as an insulator. Question A. Does the data from the graph support Dave's hypothesis? You're going to need to get some numbers from the graph to do that. And part B. How could Dave be more sure of his hypothesis? What else could he do in this practical to be a bit more sure of his hypothesis? I'm going to give you 3 minutes total. You're just coming up to a minute left, so you should be just about to get on to part B. Minute left. The only way to get any marks on part A is going to be to get some numbers from that graph and compare them. So Dave's hypothesis is talking about doubling the thickness of an insulator, so that's what we need to do with our numbers. We need to look at the effect of doubling that thickness on that temperature drop. If an insulator is doubly as effective, it means you're going to get half the temperature drop. So the numbers I've picked, I'm going to pick 0.1 millimeters. It doesn't matter if you've picked others, it just made sense for me to pick those. So I've gone up from 0.1 millimeters, I've gone up for the best fit line, and I've gone across there, and I can read from there the temperature drop. So 0.1 millimeters gave me a temperature drop of 38 degrees. Now what I've done, I've doubled the thickness. So doubling the thickness from 0.1 up to 0.2, that gives me a temperature drop of 27. So let's compare those two values. If Dave's right, doubling that thickness should have halved that temperature drop. I've picked another one to be sure, so I've doubled again from to 0.4. So from 38 to 27, 38 divided by 27 is a factor of 1.4. Now that's not a factor of 2, so that one's not really supporting Dave. The next one, from 27 to 12, 27 divided by 12, is about 2.3, so that's closer. I wouldn't say that the data really supports Dave's hypothesis, but it doesn't completely go against it either, which is why I've put question B in. So I'd say the data's inconclusive. Part B, what could Dave do to be more sure of his hypothesis? The only thing you can really do to be more sure of any hypothesis is to get more data. Now that could mean having more thicknesses. It could mean doing different materials. At the moment, Dave's only looked at newspaper. He's not looked at other materials. So even if it was perfect data for newspaper, it doesn't mean that all insulators necessarily behave the same way. So more data, more readings, more materials. Exam question then. I've just done it in 2 bits, so we're going to look at the first bit first, which is worth 2 marks. I'm going to give you a minute. I want you to have a look yourself. I'm not going to read it to you, so it's just about a ski jacket, but exactly the same principle. We're looking about heat transfer. Just 20 seconds. Part 1. Which process of heat transfer will it reduce? So it's talking about the shiny layer. There's 3 types of heat transfer. Conduction, where we're talking about heat travelling through a material. Convection, where we're talking about fluids, that's liquids and gases, heating up, expanding, becoming less dense and rising. Hot air rises, that's where that comes from. Then we've got radiation. Radiation is infrared. It's waves transferring energy from a material. So we've got a shiny surface. Which one's that? Well, that's radiation. It should reflect infrared back in towards the body. And part 2, why is the layer of fleece? A lot of materials work in the same way. They trap in air, and air that can't move is a good insulator. So there's the mark scheme. Traps more pockets of air for part 2 and radiation for part 1. Next bit, so this looks very much like our investigation. We've got three materials, N, L, K and J there. I'll let you read the 2 bits of the question, and I'm going to give you 1 minute. Okay, part 1. In each test, the water cooled fastest during the first 5 minutes compared to the last 5 minutes. Why? We always call them cooling curves. They always end up curving. They don't fall straight down. And that's because you get a greater temperature loss when there's a bigger difference in temperature. So if you've got an object at 60 degrees and the room temperature's at 20 degrees, it'll drop more quickly because there's a bigger difference. So on the mark scheme, bigger temperature difference. And part B, one other quantity that's got to be same in each test. It's important to use the same volume of water, so it's got the same starting temperature. Because it drops, the temperature drops faster if there's a bigger temperature difference between the water and the surroundings. That's why it's important to start at the same temperature. We've not got a question on it, but you can see that material M is a better insulator and J is the worst insulator. I'm just going to leave you with a summary. If you've not done this already, it's probably a good idea to write the method out. Make sure you can remember the method. In which case, zap back on the video and pause it. Pause this if you want to include more on the summary. I've got a few notes on different types of variables, diagram of the setup, and the two different sorts of curves that we've done. I've also put the required practical word for word down as it is out the specification. That's the last lesson for energy, so I'll see you next time for a different topic.